Hello and welcome. In this probability distribution tutorial, we will embark on a journey through the fundamentals of probability distributions. We will start by defining what a probability distribution is and why it's so important. Then we'll explore both discrete and continuous distributions, covering their properties, applications, and how to calculate key metrics like mean and variance. This is a live tutorial we have compiled as a complete guide to probability distributions just for you. But before we begin, make sure you subscribe to our channel and hit the bell icon for more updates on our new videos.
Okay, so I'll just quickly go through the agenda for today. See, we want to revise probability quickly, okay? So I'm sure we all understand probability, right? So the basic notion of probability, we want to revise it quickly. Then we'll go directly into distributions, both empirical and theoretical. These are two important perspectives of distributions which we need to understand. Right, then we'll talk about random variables. What are random variables? And we'll specifically get into discrete random variables. And then we'll see an example of a discrete distribution, that is the uniform distribution. Okay, and I believe in the TA session that follows this session, you will also look at some other examples of discrete distributions such as Bernoulli. Okay, Bernoulli and binomial. But yeah, so for this session, this is the agenda. Great. So let's quickly revise probability. Okay. Let's start with why probability. See, probability is obviously a mathematical concept. So first, let's talk about mathematics in data science. Now, if you look at data science and machine learning, at the end of the day, if you take a perspective look, right, you sit back and you look at this domain, all of this is working mainly because of the supporting mathematics behind all these algorithms, techniques, and models. Okay, so mathematics is actually the underlying system, or underlying, let's say, ground, okay, on which all of these things work, right? Be it mean, median, mode, histograms, visualizations, be it hypothesis testing, be it regression models, machine learning models, neural networks, whatever it is, right? Everything is working because of the underlying mathematics. In a sense, what we are talking about is measurement, right? Mathematics in the sense measurement. So for example, a machine learning model is basically just a system of numbers and operations, both mathematical, right? Mathematical numbers, mathematical operations. And human interpretation is more or less required where? It's required in the first step, it's required in the last step, maybe a little bit here and there in the middle. In fact, in machine learning, it's strictly in the first and the last step. The human interpretation and interference, so to speak, in machine learning is mostly in the first and last step. Okay, so you'll obviously look at machine learning a bit later in the program. So a model itself just strictly works on numbers and not knowledge. So we need to understand how these numbers work and how we interpret these numbers. Now let's get to a subset of mathematics, which is probability, and why it is used in data science. So see, this is your real world, okay, and you're essentially collecting data, right? So suppose this is data of heights, salaries, number of web page hits, whatever it is per day, things like that. You're accumulating all this data. There is always uncertainty associated with the nature or the value of the data, you can say. For example, if my website today say had 1 million hits or something like that, tomorrow is it going to be million? Day after, is it going to be million? Is it going to be million every day? If it was million every day, then I don't need data science, I don't need machine learning, I don't need to understand probability, nothing, right? If it was just 1 million hits and this is the truth every day, then I don't need any of this. The whole thing is that there are fluctuations in the data values. Are there patterns in these fluctuations? This is where probability comes in, right? So we need to have a strong understanding of probability, which will then allow us to properly analyze this real data, right? Instead of just looking at it without any understanding of why things are behaving a certain way, without any knowledge of, okay, this is a higher probability, this is lower probability. We don't have all this knowledge, suppose, just randomly analyzing, right? That is that gives me less insight. If you want more insights, which is what we want at the end of the day, then we have to also look at the data in terms of how they are distributed in the real world because of all these fluctuations. Okay, so some and of course everywhere we are going to have probability distributions. If you sort of look at data analysis, most data analysis in the industry, right? You'll always have a distribution mentioned somewhere. You'll always have a confidence interval mentioned somewhere, right? You'll always have a confidence percentage mentioned somewhere. It's all probability based. Why? Because there's uncertainties everywhere in market conditions, in the domain of finance, right? Probabilities of accidents and deaths, right? These are also possible things. We need to model them in terms of probabilities. Then only we can understand what kind of insurance plan we should design, right? In transportation, so I'm in Bangalore, so nowadays the probability of traffic is equal to 1. It's pretty bad, but generally speaking, over the course of 24 hours, you're going to have a distribution of traffic. It's going to go up and down, right? Same with accidents and things like that. So if you're designing transportation governance rule systems and things like that, then you need to take conscious calls, of what to do when, and things like that. In all of these domains, you have to deal with how data are distributed. Okay, so let's start from the basics. Okay, we'll start from the basics. As I said, all of these concepts and techniques cannot be done in one session. Okay, we'll have to start basic, then we'll go a little bit more advanced, then we'll go a little bit more advanced, right? So it's like layer and layer of understanding. Okay, so we'll start with some terminology, then we'll do some other things. You'll understand discrete distributions, you'll understand expected value and variance, right? Then you'll go to continuous in the next session tomorrow, right? So, and that presupposes that you know this. Okay, so it's easier to go this journey step by step. You may not be able to see the final sort of outcome immediately, but that's the nature of the course. Not the course, maybe the 2 weeks. Okay, probability and inferential stats and hypothesis testing, right? It'll take some time to be able to have all these underlying concepts so that you can immediately use it on a data set. Okay, so we'll start with some terminology. So these are things that we know, right? An experiment is essentially just a repeatable procedure with observable outcomes. So for example, very simple, right? Very simple examples so that we can understand properly. A standard fair die is rolled 10 times and the number that appears is observed. I think this is exactly what you can see here on the right side. These are the numbers that appeared on my die, and I have rolled the die 10 times. That's my experiment. Okay. So the description of the experiment actually depends on the problem statement. I have, of course, taken a very simple experiment here, right? But when you sort of do on the real data, so you may think about say traffic and things like that. The kind of experiment you do and the kind of thing that you're observing, what are you observing, that will depend on the problem statement. Okay. What is a trial in an experiment? So a single performance of the experiment is what we call a trial. You can call it trial, you can call it observation, anything, right? One experiment is performed here, right? I roll my die 10 times, that is one experiment. But in that experiment, I have n trials. So I have 10 trials in this experiment. So another way of saying that is the size of the experiment. And another way of looking at it is the number of data points in the data set. These are all same thing. Okay. And what is the result? The result is just the result of the trial. So here the result is 2, result is 1, result is 3, and so on. Okay. And one more thing, an experiment may be tried any number of times. So nobody is saying stop at 10, right? You can go on and on. It can be tried any number of times. Hence, we have the term trials. Okay, these are the basic terms. Now, some terms on top of that. What is an outcome as opposed to a trial? An outcome is essentially a possible result. So you're converting this list of results into a set. Okay, if you see the outcome, which is the possible result or possible outcomes, there are only 6, right? If you're talking about rolling the die, right? If you're talking about rolling the die, there are only 6 possible results. That's 1, 2, 3, 4, 5, 6. This is what we know as outcome. So here in this experiment, I have 10 trials, I have 10 results, but I have only 6 possible outcomes. Okay. Now, what is the sample space? I hope we all remember this, right? Sample space is the set of all possible outcomes. So you just put all these outcomes into a set, you get your sample space. And the size of the sample space in this case is 6. Okay. Compare this with this size of experiment. Same experiment, okay. This I went to the previous slide. The size of the experiment is 10. There are 10 trials, right? But the size of the sample space is 6. So keep that in mind. This will become important a little later. What is an event then finally? An event is essentially a subset of this sample space. So you have many types of events, okay? You can have elementary event, you can have compound event, so on and so forth, right? So you could have the event that the number 1 appears, you could have the event that even number appears when you roll the die. So in this case, it's just 1 element, in this case, it is 3 elements, so on and so forth, okay? Of course, all possible events may not be of interest in the real world. When you design your experiment and you collect data for that, and when you define the events, you need to look at important events which are important to your problem statement, right? All the events may not be of interest. Now, finally, I would just want to close this terminology bit with this part. Mutually exclusive and exhaustive events. Again, it's just revision. So mutually exclusive events cannot occur simultaneously, right? So 1 and 2 cannot occur, 1, 2 and 3 cannot occur. Of course, this is a very simple example, but these are events which if one occurs, the other cannot occur. And what is an exhaustive event? An exhaustive event is something, if you put those events together, it needs to make up the sample space. So here you have 1, 2, 3, here you have 4, 5, 6. If you put it together, you will get 1, 2, 3, 4, 5, 6. Same way here you have 1, 2, 3, 4, 5 and 6. If you put these 6 together, you will get the sample space. And what is the set of events which is both mutually exclusive and exhaustive? So that would be the elementary events. Okay. Any 2 events from this set, of course, they will be mutually exclusive, and all elements together in this list of events will be exhaustive. You will get your sample space. In this session, yes, Priyanka, I'll go a little slow, sure. In this session, we will focus on elementary events. Okay, so there's no need to worry about the terminology difference in, one might be called an event, elementary event, outcome, possible outcome, right? If I have to summarize this, there's a very easy way to summarize this. If you see the number 1 just written like this, then we are talking about outcome. Okay. If you see the number 1 written inside curly brackets, then we are talking about event. It's a very, very small distinction. But why is this distinction there? Because elementary events are not the only kind of events. In the die example, all the outcomes are mutually exclusive, right? But what happens if you define your event as even? So I went to the previous slide, you can see here, it says even, right? So then the question comes, are you, rolling the die once or thrice? Now, if you're doing once, then you have to do what? The so you have 1, 2, 3, 4, 5, 6 in your sample space, right? So then you're counting how many times we have 2, how many times we have 4, how many times we have 6, and then you're adding those, addition. So things get little bit more complicated in probability when you deal with events which are not elementary. But for this session and for understanding how probability is used in data science, I feel that we should focus on the elementary events. So you don't need to worry about this difference, this curly bracket, you don't need to worry about it. So let's move on to the main track now. Okay, so from now on, from this point onwards, we will focus on all the concepts and techniques that we need to understand, so that we can take this knowledge ahead to the next sessions, to the next week, and so that when you encounter things like hypothesis tests, that time we should be fully aware what we are talking about. What is the distribution? Why does the variance matter? All sorts of things, right? So let's start with the most important concept in data science, probability, whatever it is. This is exactly what we are analyzing. Okay, frequency. Frequency is essentially the number of times an event occurred within an experiment. I would request everyone to look at the rightmost column, the result column. So this is the experiment where I rolled a die 10 times. So you can see 10 observations, 2, 1, 3, 1, 6, 6, whatever, right? You can of course convert this into a frequency table, right? Now the events here are what? Number 1, number 2, number 3, number 4, number 5, number 6. And the frequency with which these events occur is what I have jotted down here, 3, 1, 2, 1, 1, 2. Okay. So the number of times an event occurred within an experiment. And the way that generally we write in mathematics is, n of 1 equal to 3, n of 2 equal to 1, so on and so forth. Okay, simple. For mutually exclusive exhaustive events, the sum of the size of each event will be equal to the size of the experiment. Okay, this is also obvious. 3 plus 1 plus 2 plus 1 plus 1 plus 2 should be equal to 10. Because where did these numbers even come from? They came from you counting, right? You counted from the result, so you got these numbers. Great. What's a frequency distribution? Now, see, the word frequency distribution, most people think we are talking about this diagram. Technically speaking, we are talking about some kind of a function, okay? Technically, what we are talking about is we are talking about a map. So if you see in mathematics, the word function can also be interchanged with the word mapping. Okay, those who have maybe remember some of these functions are also called maps in mathematics. So when we say frequency distribution, we are essentially talking about a map between the event and the frequency. Okay, this map you can show in the form of a diagram. Visually, of course, all of us will understand better, including me, right? Everyone will appreciate better if you visualize and understand these things. But we should not forget that actually frequency distribution means what? It's actually a mapping. It's actually a function. Okay, what it does? F of event equal to frequency, basically. Okay, great. So for this experiment, you can see the frequency distribution here on the left side. 1 has a frequency of 3, 2 has a frequency of 1, 3 has a frequency of 2, 4 has a frequency of 1, and so on. Okay, we'll come back to this a bit later. Now, before we move further, we will look at definitions of probability. Since probability itself is not the most, how shall I put it? It's not the most easily interpretable thing. Okay, probability is a very enigmatic thing, right? So many people have tried to define in many ways, right? So there are 4 very common types of definitions of probability which is followed all around the world. Okay, and the first is the empirical or the experimental. Basically what it's trying to say, perform an experiment. Okay, you perform the experiment and you use the frequency distribution that emerges from your experiment. Classical or theoretical is the definition where you define an experiment, okay, and then you basically assume your sample space. You don't need to worry too much about this statement. What I'm trying to say here is sample space needs to be defined. Once you define the experiment and define the sample space, you create the probability distribution from that. This is theoretical. Okay, so this is basically in school, math teachers would have told Shubham, Karan, Naga, Sai that this is a sample space. calculate the probability. And Shubham, Karan, Naga, Sai, all of you got the same probability. Why? Because you derived all those probabilities from the theoretical definition of probability. Okay. Subjective probability. Subjective is kind of niche. It's not, very actively used, but nowadays it is being more and more used. It is the measure of belief of a person. So think about surveys, think about polls, think about the end poll, right? After this session, you will be giving your feedback and things like that. That's a subjective definition of probability. And then in academic circles, where rigorous research happens, rigorous mathematical research happens, most mathematicians just combine all the three previous ones. They combine this, and this, and then they use something called the axiomatic approach. This is purely mathematical. And in this session, we will be looking at empirical and theoretical, and this will help us, set our foundations on how to use data to make conclusions about populations and things like that, right? These are the two things that we need. So I've written title here as relative frequency because that is what probability is. Okay, I want everyone to internalize that there is no difference between frequency and probability. Okay, frequency sounds like a very friendly word, frequency, number of things, very nice, right? It sounds like a friendly word. Probability sounds like some sort of a dangerous word. Oh, probability, very difficult. They are the same thing, right? In the empirical case, what you're doing, you can just read this out loud. I performed the experiment n times. I saw the event E occur n of E times. So experiment could be 10 times, event E occurred 2 times, for example. So the probability of event E according to my experiment is what? 2 by 10. Simple. That's all. This is what empirical probability is. What about theoretical probability? You can read this. I haven't performed the experiment even once, but I know how the probabilities of my elementary events are distributed. Question is, how do you know? So there are a lot of assumptions. Okay, according to my assumptions. So according to my assumptions, probability of the event E, maybe it is 3 by 10. I don't know. Of course, here the question is, where do these assumptions come from? Without doing the experiment, how do you know the probability? But of course, here you will refer to things like intuition, right? Physics, things like that. I'm sure all of us have had discussions with our peers, friends, family members, that when you roll a die, why is it that we assume that 1, 2, 3, 4, 5, 6 have the same chance of occurring? Why, right? So I'm sure all of us would have discussed this. Okay, physics, from the point of view of physics, there's nothing differentiating the one side from the two side, right? Or maybe some of us said two side has 2 dots, more ink, so it should go down more, so its probability should be less, right? Things like that. Anyway, in theoretical, there are a lot of assumptions that you're making. Okay, the whole point of today's session will be to connect these two realistically. Okay, not just connect in the sense this is point 2, this is point 3, be happy, both are equal. No, we will connect this realistically, and in the next session tomorrow we will import this to continuous distributions, continuous variables, which are a lot of the variables floating around, right? Height, salary, traffic, whatever. Of course, traffic I think is discrete with number of vehicles, but a lot of things are continuous, right? We'll connect those. And then once all of this connection is made and we fully understand how this thing works, then you will start with, sampling and then hypothesis tests, things like that. Okay, so for that we need strong base in this. So empirical versus theoretical probability. This is our discussion. Now, if you see on the left hand side, I have a table. And again, this is just the rolling of the die. I don't know how many times I rolled it here. You can check the denominator here. It says 50. So I rolled the die 50 times. As you can see, this is the actual collection of the results from the experiment. Okay. In the theoretical case, what the table is just the sample space. And sample space is a set. Sample space is a set. You see these frequencies, 1, 1, 1, 1, 1. These frequencies cannot be anything but 1. Because our assumption is that the numbers on a die have the same chance of occurring. So all the frequencies will be reduced to the same frequency, right? And then if you want, for example, probability of 2, you will say, okay, 2 is 1 out of 6, right? So this is how you calculate 1 divided by 1 plus 1 plus 1, 1 out of 6. And I get 0.17. This is theoretical. In the empirical case, if you want P of 2, you need to go back and see in your experiment how many times did 2 occur. It occurred 9 times. And how many times did you throw the die? 50. So 9 by 50 is 0.18. Well, of course, they look similar, 0.18, 0.17. But then I told you, I would like to convince the audience today that it's not just coincidence that you're getting, equal. There is some kind of law at work. Now, how do we really interpret probability, generally speaking, right? What is the interpretation of this thing? So, so obviously I am taking this session for an audience who is well versed, with these concepts and the real world and day to day whatever we do in our work, right? So when I used to teach, let's say college kids, younger kids, right? That time I used to tell them that there is no interpretation to probability, because that's all I could tell them, right? They wouldn't understand the implications of this, right? But now we are here, right? So what is the interpretation of probability? See, most people say it is measure of likelihood, this is kind of textbook definition, right? Measure of likelihood of occurrence of event. Okay. Honestly, to me also, what does it mean, right? It's honestly not very useful if the number of trials is low, right? So it's like this. If somebody did an experiment for 10,000 times and they got some probability of 0.6, they say, oh, 0.6 is greater than 0.5. It's a positive probability. You perform your experiment once, you will get the result. No, right? That's not how probability works. Probability, if you want to interpret, you have to think in terms of large numbers. You actually have to think in terms of large numbers, right? So consider this case of, coin toss with increasing number of trials. So here I have 1 trial, 5 trials, 10 trials, so on and so forth. I'm also recording the number of heads, number of tails each time, and therefore you can get the probability, right? Just divide by the total. What you will see is some kind of fluctuation, right? Initially it will fluctuate 1.4, whatever, and then it will slowly come down to 0.5. Same thing for the tail probability also. It will fluctuate, and then it will come to 0.5. So you need to do this experiment so many times, then only you will observe similar results, right? And this is true. If I have to translate this into, for example, business language, just because I sold one product, I cannot make a comment on whether it was profitable or not, whether the project was profitable or not, whether the enterprise was profitable or not. I cannot comment. I need to sell thousands and thousands, maybe even hundreds of thousands of the product, and then I have to see in terms of probability analysis, was or will it be profitable, will it not be profitable. All of this has to be done not in terms of selling one product, right? You have to sell multiple, and all of that, whether to sell, how to sell, what is the selling price, what's the price point, all of that you need to do proper probability analysis, right? So large numbers, keep that in mind, large numbers. Which takes us to, empirical and theoretical distributions. How do we connect these two things? First of all, what's a probability distribution? So just recall this dice experiment in which I, rolled the die 10 times. These are the events, these are the frequencies. I have my frequency distribution here. Great. All I have to do now is divide by 10, correct? I just need to divide by 10 all of these frequencies. So how do you compute probabilities? Empirically, just divide by the total. So you convert the frequencies into probabilities. 3 by 10 becomes 0.3, 1 by 10 becomes 0.1, so on. And your distribution is going to look like this. This is a probability distribution. Okay, more or less the same thing. I guess all of us right now are thinking it's the same thing. Yes, more or less it's the same thing. Correct. So in terms of empirical methods, frequency distribution and probability distribution will be the same thing. Okay, they are the same thing, more or less. So if you can see, the two shapes also look similar. You just scaled it down by a factor of 10. How do we move from this empirical to theoretical? Okay, so this is a question to the audience again. I guess this is my 10 size 10 experiment rolling die. So this is n equal to 10, I think. My question to you is, just imagine if n is infinity. What do you think will happen to this probability distribution? Will it retain the same shape that you're seeing here? You may put your answers in the chat. So this is me rolling a die infinite times. And for the sake of, for those who are realists here, suppose 1 million times. Okay, I roll my die 1 million times. So just imagine that after rolling it so many times, yes, what's gonna happen is it's gonna become flat. Now you can try it out, right? All of us do have this intuition. As I said, when we roll a die, our assumption, our internal assumption says each of those events, 1, 2, 3, 4, 5, 6, they are equiprobable. There is nothing special about 2 or 1 that it should occur more number of times. That is what we would call a biased die or a loaded die. Okay, this is a standard die, normal die. So point is, when your number of trials is less, okay, you cannot make too many conclusions about your experiment. Not possible. You need to have a large number of trials, and if you do increase your number of trials a large number of times, you will see that this specific experiment, it's going to become a flat line, as Palash said, as Subodip said. And essentially speaking, every empirical distribution is actually an imperfect copy of the same theoretical distribution. Now this theoretical distribution, which we will study at the end of the session, this is called the uniform discrete distribution. Okay, uniform, which means all the events have the same probability. What is the example of uniform? Throwing a die or tossing a coin, right? These are all uniform. In fact, if I told the audience right now to choose a number between 0 and 9 and put it in the chat, and I get those numbers and I make a distribution, that is also uniform distribution. Why? Because there's nothing special about number 3 that Subodip likes number 3 so much he'll keep putting 333, right? Or say, in general, the class has, I think, 27 people. Yeah, we have 27 people. So there's nothing special about the number 3 that out of 27 people, 7 people go for 3, 20 people go for 3. Nothing special about the number 3. So if I told the audience right now, choose a number between 0 and 9, I will generally see a kind of, flattish, this kind of thing. And if we had more audience, if we say 100 or 1000 audience, then it will more or less settle in this. Okay, this is what we call a uniform distribution. So the empirical distribution is an imperfect copy of the uniform distribution. Notice how the tables have turned. Okay, initially we said theoretical distribution, assumptions, no real substance there, right? But if you keep doing the experiment many times, you will see that the empirical one goes to the theoretical one. There's a very strong connection there, right? So theoretical probabilities can be estimated by performing the actual empirical event multiple times. Okay, now why is this important? Why exactly is this connection important? See, once a type of experiment has been performed and performed enough number of times, and you have a resulting distribution which has been studied and verified, you don't need to perform the same experiment ever again. Okay, people in the past have done this, right? They have rolled a lot of dice, they've tossed many coins, and they've done all sorts of experiments just to verify, okay, that are these things matching with the theoretical claims, and they do. Okay, and that's quite an interesting point. It's not practical to build frequency tables when you have large populations of data. It's just not practical, right? For each experiment, you might be dealing with 10,000, 100,000 data points. So for each one, counting each time, and then making a frequency table, all of that, unnecessary. As long as you make some safe assumptions about the population, then this connection between this empirical theoretical, which is n approaches infinity, right? Which means if you have enough sample size, if you have enough population size, then you can make safe assumptions and you can completely ignore the empirical distribution. You can directly work with theoretical distributions. There are of course even more advantages, which we will deal in the next session tomorrow. Okay, as I said, all these things cannot be covered in it's kind of a wide subject, right? So we'll again touch this point when we do continuous distributions, as I'm saying here, which is what I've said in this bullet point. I think this becomes even more important in the case of continuous distributions, right? You cannot keep collecting data about continuous variable till its distribution is good enough. For example, if I ask you, can you tell me generally what are the probabilities of human height, right? Heights of humans, right? Can anyone in this audience let me know what is the mean height, let's say, of Indian people? That you can Google and find out. But if I told you, you should find out, not Google, then just imagine how hard that is. Okay, just the mean. Then if I ask you, find me the probabilities of each of those things. Find me the probability of 168.2 centimeter. Find me the probability of 161.4 centimeter. Can you imagine the kind of data that you have to work with? So when you're dealing with large populations, there are certain techniques that are used in data science, which allows you to skip collecting and working with the data of the population. This is exactly what we call inferential statistics. Okay, and what we are studying now, which is the connection between this empirical theoretical, this allows us to perform this thing that we call inferential statistics, where we make certain safe assumptions about the population and about the distribution, and then we are able to do meaningful experiments. Okay, anyway, we will deal with that. Right, so let's move on to discrete random variables. Okay, so till now we've understood probability, we've understood probability distributions, which is essentially map between the outcome or the event and the probability of that event. And we also had a discussion around empirical distributions and theoretical distributions, and we also concluded that if you perform this empirical the experiment enough number of times, then the probability numbers that you get, they will start to flat out. At least in the case of the rolling of the die, it will flat out. Of course, other variables need not be uniformly distributed. There are many types of distributions, and in the next session we'll see other types of distributions. But the point is that there is there seems to be some kind of a connection if you perform an experiment enough number of times, and if you get the theoretical probability using assumptions, whatever logic, right? There seems to be a connection there. Okay, so this is what we've studied till now. What are random variables? Okay, now again we've heard this word many times, random variable, right? So let's get into it. What I would like to say though is it's not necessarily a new thing. See, a lot of the things that we are going through now in the discussion of probability distributions, right? It's just new terminology for the same thing. So a random variable is essentially a quantity or a variable whose probability of occurrence can be associated with a probability distribution, essentially the x-axis. Okay, if long story short, what we are talking about is the x-axis, right? Now, in the simple case, you will call it event, outcome, so on and so forth. In mathematics, we try to generalize and we call it a random variable. So for example, in the experiment of rolling a die and observing the number that comes up, the RV is the number that comes up because that is what you're observing. Okay, then next one, toss a coin, observe what symbol comes up. The random variable is the symbol that comes up. And suppose we have an experiment where you choose a person at random and record their height, right? Here the random variable is the person's height. So random variable is essentially the thing that you're measuring in an experiment, right? Now there are two kinds of random variables, discrete and continuous. Discrete will take exactly one value out of exactly some finite number of possible values, right? Continuous random variables may take any numerical value. So example of discrete is number on the die. Okay, number on the die. This can be 1, 2, 3, 4, 5, 6. Example of continuous, many real variables are continuous. Height, salary, anything, weights of babies, all of these can take any numerical value. Now the first session is on discrete for a reason. Okay, we could have started with continuous, right? I could have easily just started with heights, continuous distributions, formulae, integration, whatever, right? I could have, but I feel that if we understand certain concepts using discrete, it is easy to understand those when you go to continuous. The math in the continuous is little bit more complex, right? So sometimes we lose out on the ability to understand what's going on. So it's always better to start off with discrete and then move to continuous. Okay, so again, new terminology, PMF, right? PMF. So why so much terminology? That's kind of the way it is. You know, as I said, you might be seeing a slide in front of you called PMF, probability mass function, as if it's something new, but it's not. It's not something new. Okay, so initially this is what we had. You rolled your die 10 times. These are the possible events: 1, 2, 3, 4, 5, 6. These were the frequencies you recorded: 3, 1, 2, 1, 1, 2. When you performed the experiment 10 times, you converted the frequency to probability. Now if you see on the right side, you have the exact same numbers. Okay, these are exact same numbers. So here 1, 2, 3, 4, 5, 6. Here you have 1, 2, 3, 4, 5, 6. Here you have the probabilities: 3 by 10, 1 by 10. Here also you have the probabilities: 3 by 10, 1 by 10. So the only difference is now we are saying, instead of looking at each event as a separate event, rather we are looking at each event as a value of a variable. If you remember in the beginning of the session, I told you that essentially these distributions are functions, right? These are functions, and in the full mathematical sense of the word, right? If we remember relation, function, and all of that stuff from school, these are actually functions. So we say that there is a variable x who takes these values 1, 2, 3, 4, 5, 6, who takes these values, and we associate a probability of having those values. So x and p of x. Essentially what you've done is informal, you moved from informal to formal. That's all. You moved from informal to formal. Now the reason for this is we want to do a lot of computations, right? We cannot keep talking in informal terms each time. So to formalize and universalize all of these things, we use this notion of probability mass function, which is a function, and we use this notion of random variable. Okay. So I'm showing here a PMF for an empirical distribution or empirical case. Generally speaking, people directly use the concept of x and p of x with continuous case. Okay, so I'm just showing it for empirical for the sake of understanding. Generally, when you see random variables, they are associated with theoretical distributions. Okay, not with empirical distributions. Okay, so the empirical one is sorry, 1 second. Yeah. So what did we do? We essentially went from event and probability. We went from event and probability to random variable, okay, x, and its probability mass function p of x. Okay, and as you can see, the tables are essentially the same. The only reason we did this is because we want to do computations. All right, so now you know what, let's actually put all of this into action, and we'll take up a simple experiment and we'll try to investigate it. Okay, see, suppose that a biased coin was confiscated from a gambling house. Okay, now the gambling house obviously allows for gambling, right? The game that was being played using this coin was a very basic coin toss game. Okay, if a player gets a head, they win $10 from the gambling house, but if the player gets a tail, they will lose $5 to the gambling house. Okay, now on the surface, this is the information that the public has, correct? This is the information that the public has. If I win this game wherein I'm just tossing one coin. If I win the game, I will get $10. If I lose the game, I will lose $5 to the gambling house. Okay, so on the surface, this looks profitable. This looks good for me, right? Heads equal to $10, tails equal to lose $5. This looks good for me. Now, the gambling house was suspected that, okay, there was some suspicion that something's going wrong here. So this coin was confiscated, okay, say by some authorities. What they did was they tossed the coin sufficiently large number of times in a controlled environment. Sufficiently large, please imagine 10,000, 100,000 number of times. Okay. Now, ideally, if you do that, one might expect that your probabilities for head and tail should come 50-50 or at least near 50-50. But it was found out that the head probability is 0.2 and the tail probability is 0.8. Okay, which means the coin is biased or unfair. Now, of course, a coin in a gambling house is going to be biased or unfair, but just how much bias, how biased or unfair, that's what we are trying to look at. Okay, so the gambling house is justifying this biased coin, saying that winning amount is larger. They are saying, okay, winning amount is $10, losing amount is $5. Why do you have a problem? That is how the gambling house is justifying. So how are you going to tackle the gambling house? How are you going to go and say, no, this is not fair, or there is a problem here, right? You have to speak in the language of numbers. First of all, let's convert this situation into a mathematical model. Can we define a random variable and describe a distribution for this case? Yes, we can. Okay. So the event is essentially getting a head, getting a tail. The random variable is the value we are interested in. Now, the game says what? If you get a head, then you will gain $10. So that's plus $10. Okay. If you get a tail, you will lose $5. So this is minus $5. This is the random variable in this game or experiment. The amount of money, okay, going from the user or the player. So in the head case, the player gets $10. In the tails case, you will lose $5. So this is our random variable x. What is the probability mass function for this x? For heads, we know that the theoretical probability, note that I've written here sufficiently large number of times we have tested this coin and we have observed p of h equal to 0.2 and p of tails equal to 0.8. So these are theoretical probabilities. Okay. So for the head, it is 0.2. That is 1 out of 5 times, right? And for tails, it is 0.8, 4 out of 5 times. This is your distribution. This x and p of x combination is the complete distribution for this case. Okay. Plus $10 with a probability of 0.2 minus $5 with a probability of 0.8. Great. Now, how do we start analyzing this, right? How do we say 0.2 is bad, 0.8 is bad, this is good? How do you even start talking about these things? What is the language? So there are certain things, certain metrics that we should be familiar with, and this will become more important as we go deeper into inferential stats and things like that. Let's start with expected value. Okay, so suppose I'm asking the question, is the gambling house looting the public? Okay, one way to find out is empirically. You play the game a lot of times using a lot of players, right? Now, what we can do is we can create a team of undercover investigators, say 10 people, right? 10 people from the authorities, undercover, and you just send them to the gambling house, tell them to play the game for a large period of time, many games. Tell them to play many games and then see what happens. So from this, we will be able to see out of the 10 investigators, how many were able to win money, what is the distribution of how, are people winning, losing. One way to do that is just go and do it many times. So suppose we have these results from one investigator. Okay, so we know that our random variable is this plus $10 minus $5, and this investigator played 100 games. Okay, suppose this investigator played 100 games. So here you have frequency. The investigator won $10 25 times and the investigator lost $5 75 times. What is the total loss or profit of the investigator? That's the first statement here. It's very simple. If I gain $10 25 times and then lose $5 75 times, that's just 25 into 10 plus 75 into minus 5. Just multiply and add. Answer is minus 125. Totally, this investigator lost minus $125. What is the average loss? So how many games did the investigator play? 100 games. So minus 125 divided by 100, right? 25 plus 25. So you're getting minus 1.25. So on an average, this investigator is losing minus $1.25 per game. Minus $1.25 per game. Okay, my dollar sign, yeah, minus $1.25 per game. I've only used the frequencies. The point is that you can convert the frequency into probabilities. So you know that your experiment size is 100. We've already studied before how to get probability from this. So 25 divided by 100 is 0.25. 75 divided by 100 is 0.75. So the same equation, if I just divide it by 100 everywhere, if I just divide by 100, you will get the same answer. You will get minus 1.25. So instead of frequency, you can use probability, right? So if you see in the last equation, I am using the probability 25 by 100 into $10 plus 75 by 100 into minus $5. That's essentially 0.25 into 10 plus 0.75 into minus 5, which is 2.5 minus 3.75, and you will get minus 1.25. So you can directly use the probabilities with the value of the random variable to find out on average how much the investigator is winning or losing. So this investigator is losing $1.25 per game. Suppose we have results from other investigators. Now, as you can see, this investigator played 200 games, which is why the frequency is 40 plus 160 is 200. This investigator played 1000 games, 180 games, 820 games. So you can just convert these things to probabilities. 40 by 200 is 0.2. And 160 by 200 is 0.8. 180 by 1000 is 0.18, and 820 by 1000 is 0.82. Then you use the probability values, right? So P of X, you use that. Where is that? 0.2. 0.2 is my probability of what? Of winning $10. So 0.2 into 10 plus 0.8, which is the probability of losing $5, which is into minus 5. So this investigator is losing $2 per game on average. This investigator is losing $2.3 per game. So this is one way that you can try to make a case, right? One way that you can gather evidence and proof, which, the gambling house will be forced to look at. If all 10 of your investigators, even after playing 1000 games, say 10,000 games, on average, if they are losing to $2.3 per game, then you can go to the gambling house for that. But we want to be more efficient. The whole point is we want to be more efficient. We don't want to send investigators, and do this 1000 times and things like that, right? We don't want to go around the whole country trying to gather the data of everyone just so I should, build a product, right? We want to be efficient about this. So what did we do? If you remember initially, these probabilities 0.2 and 0.8, we estimated that these are the theoretical probabilities of tossing the coin. How did we do that? We just tossed the coin a number of times. Rather than having somebody go and play the game, we just took the coin and we tossed it a large number of times. From that, we estimated the theoretical probabilities to be 0.2 and 0.8 for winning and losing respectively. This is where the notion of expected value comes in. Okay. Expected value is nothing but the same process that you have been doing till now. All of these calculations are averages, right? Expected value is when you use the theoretical probability and not the empirical probability. In these cases, you were using exactly the probability values that you got from the investigator who went out there, really went out there. These 1000 games really happened, and you have 1000 data points, on a sheet, on a sheet of paper or whatever, right? You have real data here, right? Investigators went out there. In this case, in the expected value case, investigators are not going anywhere. You just take the coin, estimate the theoretical probabilities. You know the rules of the game, right? $10 if you win, $5 if you lose. And all you do is you plug the same formula. If you see the formula here, X, this is the value. So $10, $5, these are the X values, and the probability of such X value occurring, theoretical probability. Generally, people shorten it down to this sigma x p of x. And in this case, E of x is what? 0.2 times 10 plus 0.8 times minus 5, which gives me minus 2. Now, if you see all the empirical values, here I have minus 2 as a value, here I have minus 2.3 as a value, and the first investigator has minus 1.25 as a value. All of these are close to this number, and essentially the claim is that the closer the empirical probabilities get to the theoretical probabilities. When will that happen? That will happen when your experiment size is larger and larger and larger. So the first guy, the experiment size was only 100, right? The second person 200, the third person 1000. If the number of times that a person plays goes to 10,000, 100,000, then your empirical probabilities, these values, here you have 0.18, 0.12, these empirical probabilities will get closer to the theoretical probabilities. And the moment that happens, what will happen? The averages that you are calculating here will actually be much, much closer to the expected value. That is the theoretical expectation. It will be very close. This is what we call in mathematics and specifically in data science, this is what we call the law of large numbers. Expected value in which you are using theoretical probability is getting close to the mean, which is the real average, right? These two will join. When will that happen? When n tends to infinity. Okay, so essentially, instead of going and investigating using investigators, I can replace that whole process with the theoretical probabilities. I don't need to send anyone anywhere, and I have a value in my hand. So through these calculations, I can say, hey, look, the expected value of any person playing the game is minus 2. That means, conceptually speaking, if anyone plays this game for a large number of times in the gambling house, they will lose $2 per game average, right? And that may not even be sufficient. That may not even be close to the price of the game. Maybe the price of the game is much less. Why should you be losing $2 for each game, right? So expected value is the general or the long-term experiment. The key difference I want the audience to understand, the key difference is the probabilities that you're using here are different. Okay, these are empirical probabilities. You went out, you did the experiment, you got the frequency, you divided by the total. That's how you got 0.18, 0.82. That is different from these two. These two are not the probabilities of the game. These are the probabilities of the coin. You estimated these, right? And you're using this for any game, any future game, you're using the same probability, 0.2, 0.8. Okay, that's the difference. I hope that part is clear. Here, if you see the P of X values, it's not 0.2, 0.8. Okay, not at all. Because for each investigator, the number of games they played, how many times they win and lose will be different, or the proportions will be different. But here, we are directly using the theoretical probabilities, which, you just toss the coin, say 10,000 times, and you get very close to the theoretical estimate. And therefore you don't need to play the game as such. Now see, there is strong proof and strong mathematical justification is there, okay, for this stuff, law of large numbers and things like that, but that's more or less out of scope of the sessions. So if those who are interested can go check it out, but a word of caution is there will be a lot of mathematical language, sigma and all of that stuff. But as long as we all agree, okay, if I perform an experiment large number of times, then the empirical probabilities which I calculate from each distribution, all of those will get very close to the theoretical probability, if we understand this concept, then we are good to go. This is called the law of large numbers. Okay, so the data shows that the game is designed to make money from the public in general. Okay, this is fair. This is fair because of course the gambling house is offering the gaming services, right? They are letting you sit down, play a game, blah blah blah. So this is fair. Now the question is, okay, even if we say it's fair, there is something that we can also, there's another layer of in the case that we can add. We'll get to that soon. Before that, one thing I would like to reiterate, note that if you have the theoretical probabilities, there's no need to conduct all these experiments with the investigators. All of these things are not required. This saves a lot of time, a lot of resources, and essentially you're speaking about large populations in a meaningful way. You're making predictions about the future. Okay, expected value. Now, variance and standard deviation. This is another thing that everyone has encountered, right? What exactly is variance, standard deviation? Now, again, let's ask this question. Is the gambling house looting the public? See, if the results experienced by different people who play the game are varied, right? Some lose, some win, some lose less money, some lose more money, so on and so forth. Then people are less likely to feel that they're being cheated, correct? It's supposed to be a random thing. A gambling activity such as these, or a gambling game, should be random in the outcomes. On the other hand, if everyone who plays the game, even for a small amount of time, ends up losing similar amount of money, this is what we saw: minus 1.25 average, minus 2.3 average, minus 2 average, and theoretically the answer was minus 2, right? Then it's quite apparent that there is some mischief going on, right? If everybody is losing similar amount of money, then there is some mischief going on. Essentially, a high variability in the results is generally expected from a gambling game, not consistent results. Okay, again, see, we can do this investigation empirically, but as stated earlier, theoretical methods save us time, right? So we'll directly use the theoretical distribution. And what is the theoretical distribution? This much. This is your theoretical distribution, correct? These probabilities were estimated by just throwing the coin infinite number of times or sufficient number of times. Then the same probability will be used for the winning and losing values. This is your theoretical distribution. We also calculated the mean already, not mean, sorry, expected value. But of course, mean and expected value become the same for large number of experiments. Anyway, expected value is minus 2. What is variance? So the formula for variance is pretty simple. You find the deviations from the mean or the expected value of the actual value, right? So this is plus $10. This is a win of $10, right? And the average expectation is losing $2. What is the difference? 10 minus minus 2, that is 12. Okay, here the value is losing of $5 minus $5, and the mean is of course minus 2, or the expected value is minus $2. What is the difference? The difference is minus 3. And then you square these two. So 12 square is 144, minus 3 square is 9. The squaring is done to remove the negative sign, so on and so forth. Okay, so once you have these delta x square, that is the deviation square, variance is nothing but the expected value of the square deviations. That's all. It is the expected value of the deviations. In a very, very basic sense, it is the average deviation, you can say. It's kind of like the average deviation from the mean. This allows you to define something called variance. Now see, when you say deviation, you have to deviate from something. That's why the mean is involved. Why is it x minus e of x? It could be x minus anything. It could be $10 as compared to $100, but $100 is a random number, right? It makes sense to compare the actual random variable values and how much they deviate from the expected value. It makes sense. This is why they are called deviations from the expected value, deviation from the mean. Okay, so you're finding the expected value of the square deviations. So this is expectation on top of expectation. Yeah. Okay, so again is the same formula. What is the probability of a certain value of $10? What is the probability? multiply that with the square deviations 144. So in this case the variance is what, 0.2 for winning, right? And the deviation square in that case is 144. 0.8 for losing, and the square deviation is 9. And you calculate all of this, you will get some number 36. Now, not to worry too much about this number 36 right now. Okay, I will of course comment a little bit on how to interpret this in this case, but as we go on to the continuous distributions and things like that, this will become even more clear. And in fact, when n of s is larger, this kind of I've written on the bottom of the screen. The key takeaway here, or the key observation, what we want to remember is, technically speaking, higher variance means that the results are more scattered away from the mean. Okay, so in this case, our expected value or the mean, that is -2. Higher variance means that whatever results you have are scattered away from this -2. Lower variance means that the results will be close. So when you perform this experiment, right, again I'll take the last three names I can see: Ashutosh, Nagasai, Shubham. When you perform this gambling experiment, say 100 times, 200 times, 500 times, if this experiment had a lower variance, right, then Shubham, Nagasai, Ashutosh will see similar results. If the experiment had a higher variance, then you will be seeing different results. Okay, this is the importance of variance. And let's look at the comparison, right? So if you see here, what I have done is I have only changed this. This is the default case. This is new 0.5, 0.5, and this is another case 0.3, 0.7. Everything else is the same. The event and the winning losing value, all of that is the same. In the first case, we know the mean or the expected value is -2. We know variance is 36. Okay. What if I change the probability to 0.5, 0.5, right? Somebody might say, why is the coin even loaded? Why don't we use a normal coin? Okay. So if I use a normal coin, 0.5, 0.5, then the expected value becomes 2.5 and the variance actually becomes higher, 56.25. Okay. Very interesting. So in the second case, the public is winning money, right? Public is looting money from the gambler, right? Because the average, the expected value of the experiment, anyone plays the experiment per game, the gambling house is going to give you $2.5. That's what this means, right? So that's weird. First of all, why should the gambling house donate money, right? That's weird. But interestingly enough, the variance went up. This is a good thing, right? This means that people will be getting different results. Good thing for you, of course, but bad thing for the gambling house. So, okay, then maybe you say, look, you have to use a loaded coin. You cannot use a normal coin, because otherwise how will you have fun? How will you have winning is more amount than losing? That's where the fun comes from, right? So then suppose we tweak the probability to 3 and 7, 0.3 and 0.7. Okay. Suppose we load the coin. In this case, the expected value is -$0.5 and the variance is 47.25. This is middle ground. This is middle ground. So here the public is losing less money on average. Still the gambling house is making money because the expected value is -0.5. So gambling house is definitely making money. Variance is also higher. Okay. It feels like a random event, right? It will not feel as though everybody is losing the same amount of money. So this is the middle ground in this case. I would like to tell the audience that, look, this is just two outcomes, right? H and T. When you work with mean and variance and events which have multiple possible outcomes, then you will see these concepts even more solidified, right? But I'm giving you the core essence, the meaning of these things. All right, meaning of these things. I'll not spend too much time on standard deviation. See, the table is exactly the same. So I'm just going to keep my video on because table is the same. Standard deviation is nothing but it's the square root of the variance. The only reason that we do this, it is easier to compare the standard deviation and the actual random variable. So when you do the variance calculation, the units are squared, right? So you take the square root, you get the original unit. So in this case, dollar is the original unit. You can think of standard deviation as some kind of comparable to the dollar unit. So $6 or something like that. You can think of it like that. Okay, not exactly, but it is comparable. Again, this will also be, this will be even more sort of expanded on in the continuous distribution session. Okay, you can see similar results for the standard deviation also. Same thing, like previously we saw the tweaking of the probabilities, right? And we saw the expected values of the games. Here, standard deviation is nothing but square root. 36 square root is 6, da 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 da, right? So out of all of this, if you see these three tables, most people will sort of agree that we should tweak the probability to 0.3, 0.7, and this coin is unfair. The 0.2, 0.2 is unfair. Another way to tweak, obviously you can tweak the winning and losing values. That also something you can tweak. Yeah, whatever it is, you have to tweak something. That's essentially the learning that we are getting from this. Okay, so let's summarize. Is the gambling house looting the public? See, the gambling house is playing a game with the public whose expected value is loss of $2 for the public. The variance of the game is relatively low, or the standard deviations lower than other possible cases, right? This means that in general, outcomes of the game are closer to the expected value. If this was unintentional or done unknowingly, then the gambling house should have noticed this and you should have fixed the issue. Either you make it an almost zero mean game, like in this case, almost zero mean game, right? Or you at least increase the variance, right? But yeah, if neither of this is being done, then surely you can build a case and sort of, take it with the gambling house. So quick summary, what is an expected value? An expected value is the overall general expected results of an experiment. You are using theoretical probabilities in this case. It is more informative than a weightless mean. Of course, if you just take the values and take the mean, so $10 minus $5 divided by 2. What is this? This is $2.5. Clearly, this is far from the truth, right? $2.5 is wrong. Okay, it is way more informative than a weightless mean. Sorry. It's not just any number. Okay, if you perform an experiment consisting of multiple trials multiple times, you will sooner or later obtain the expected value. Okay, law of large numbers, LLN. Those are interested can Google this and read about this a little more. Now, the only issue with the expected value is it does not give you information of the risk, right? So this is what we studied, variance, which tells me, are the outcomes going to be different for different people in general, or are all the outcomes going to be similar for different people, right? Risk, variance, that is not given by expected value. That's given by variance and standard deviation. Okay, the uniform distribution. And we've already spoken about this, right? Examples of uniform distribution: rolling a die, asking the audience what color they like, what number you want to choose. There are, and in the real world, continuous uniform distributions also, there are a few market conditions, some things like that. We'll see that in the next session. Tossing a coin, all these kinds of uniform. What is the common thing in all of these activities? What is common? Each event is equiprobable. That's what is common. So suppose that your sample space has n elements. Okay, so this is the number of elements, small n, or outcomes, and these n events are equiprobable. So basically what I'm saying then, that the probability of each event is 1 divided by n. That's it. If I have 2 events, then it's 1 by 2, heads and tails. If I have 6 events, then it's 1 by 6, rolling a die, 1, 2, 3, 4, 5, 6, 1 by 6. If I have 52 events, like the card that we discussed, the shuffle deck of cards, then it's 1 by 52, right? So many of these things are uniformly distributed. And of course, this is what your distribution is going to look like. This is your probability mass function. Each of these events, E1, E2, E3, it is mapped to the value 1 by n. Okay. So not all real variables are uniformly distributed. This is something we need to keep in mind, but many of them are. Now, in data science and mathematics and general scientific domain, this is the way we refer to it. Okay, so capital X, and then you have this tilde operator, UN. Okay, that's what I've written here. So how do you read this? X follows a uniform distribution of size n. This is how you read this statement. Okay, the random variable X follows a uniform distribution of size n. Okay, so yeah, here are some examples, right? Rolling a fair die, tossing a coin, picking a card, random number generation. So random numbers also use certain uniform distribution to generate. randomness, right? Lottery analysis, this is also can be modeled as a uniform distribution. So wherever you have equiprobable outcomes, you can use the uniform distribution, right? Okay, quickly we'll just look at the formula for expected value and things like that, just so we can solidify our understanding. Okay, and then we'll wrap up the session. So if, let's say, a random variable x is distributed uniformly and it belongs to the possible outcomes 1 2 3 dot 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 till n, so these are the values. Okay, 1 2 3, these are the values. Then you can quickly calculate expected value. It's very simple. It's x into p of x. So 1 into probability of 1, 2 into probability of 2, 3 into probability of 3. But we know that each of the probability is 1 by n, right? Because it's a uniform distribution, each of the probability is 1 by n. So you're essentially just doing what? 1 plus 2 plus 3 dot 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 till n divided by n. And this is an arithmetic progression. We remember the formula, n into n plus 1 by 2. And you have this n in the denominator. So finally the answer is n plus 1 by 2, right? The answer is n plus 1 by 2. So you can just use the formula for expected value in this distribution, and you know what is the expected value of a uniform distribution. So you can even quickly do this, right? What is the expected value of a coin toss? Very simple. Coin toss, number of possible outcome 2. So just put 2 inside here. 2 plus 1 by 2, right? 3 by 2. If you put heads as 1 and tails as 2, right? The answer will be 1.5. It's exactly between 1 and 2. Suppose you take dice 1 2 3 4 5 6. What is the number of possible outcomes? 6. So just put the 6 in the end. 6 plus 1 by 2, 3.5. So very quickly you can get the expected value of a uniform discrete distribution. Similarly, and I won't walk through the proof, you can try to work it out yourself. Similarly, the variance of this random variable, if you name your values 1 2 3 till n, the variance will be n square minus 1 by 12. Similar derivation. Okay, you can use arithmetic progressions and all that. So quick example of rolling die, we already saw this. E of x will be 3.5 and the variance is 2.9. Standard deviation is 1.7. Again, I'm not going too deep into outside the meaning of what we discussed a while ago, which was expected value being the long-term result, variance being how these results look like for different instances of the experiment. This is what we learned in the second part, right? There is more actually. There's more to these things called variance, standard deviation, right? Those points will pick up in the continuous distribution session.
In today's rapidly evolving business landscape, machine learning and AI are no longer buzzwords. They are essential tools for staying competitive. Are you ready to lead the AI revolution in your industry? Upgrad, in collaboration with IIIT Bangalore, brings you the Executive Diploma in Machine Learning and AI. This program is designed for ambitious professionals like you, seeking to leverage AI for strategic decision-making and innovation. Gain hands-on experience with cutting-edge technologies, learn from renowned faculty, and network with industry peers. Elevate your career, drive business transformation, and position yourself as an expert in AI. Enroll today and future-proof your career.
So the agenda for today, we'll obviously start off with continuous random variables. Last time we discussed discrete random variables. These are essentially just the metric or the variable that you are measuring in a certain experiment. It could be somebody's salary, it could be somebody's height, it could be the number on the dice, it could be any of these things that you're measuring. And essentially what you're interested to see how random are these and are there any patterns in their distribution, so on and so forth. And last time we saw something like the uniform distribution, and of course there are other kinds of distributions also, right? And a distribution for a random variable is essentially a pattern, right? It's so that we know that, okay, this value will come with this probability, this value will come with this probability, right? We know that. So that's what we studied last time. So this time we'll go with continuous. We will then study the uniform continuous distribution. We'll get a sense for, exactly how do we work with probabilities when we are talking about continuous random variables. The uniform distribution, discrete one we saw last time, and this time we'll see the continuous one. So fairly simple distribution to get a sense of the operations and computations, things like that. Then finally, we'll discuss one of the most important, if not the most important, kind of distribution in data science and in general statistics also, which is the normal distribution, also known as the Gaussian distribution. Okay. So part one, continuous random variables. First of all, let's look at the type of random variables. As we just discussed, there are discrete random variables. It takes exactly one out of a finite or countably infinite number of discrete values. Okay. So some examples can be rolling a die and observing the number that comes up, tossing a coin and observing what symbol comes up, observing an inbox and counting the number of spam emails, right? All of these are discrete. So when you put, for example, the spam email, right, your x-axis is going to be 0 spam email, 1 spam email, 2 spam email, 3 spam email, and so on. There's no such thing as what is between 2 and 3, 2.5 spam email. That doesn't exist. But in the case of continuous RV, this process does not work, right? This continuous random variable takes exactly one out of infinite number of values, okay, on a continuous scale. So think in terms of, choosing a person at random and recording their height. So one person may have 162 centimeter height, another person may have 163 centimeter height. So does that mean that nobody has 162.5? No. Definitely there may be somebody with 162.5 centimeter height, right? Same, another example is choose a bottle of juice at random from a supermarket, record the amount of juice in it, how many milliliter, right? These have values which you cannot fix in discrete way. Okay, you cannot fix it in this discrete way. And of course, salary also follows the same pattern. These are continuous random variables. Okay, so random variables that take value from continuous scale of values, height, salary, time, revenue, so on and so forth. Potentially, there are infinite possibilities. So now comes the problem. See, in the previous session, we were saying things like, what is the probability that the number 3 comes up in my dice roll? Or what is the probability that I have 2 spam emails in my inbox, right? It makes sense to ask that question. But I would like the audience to think right now, does it make sense to ask what is the probability that a person has height of 165.3 centimeter, right? Or let us say, what is the probability that a person has a height of 165.45 centimeter? Are these meaningful questions? Does it make sense? Can we keep asking these questions in terms of probability? The answer is no. Then the question is, how would the probability distribution of these continuous random variables be built, right? So we cannot keep asking these questions in decimal points, right? These are continuous numbers. So then how would we build a probability distribution? So before we go into that, let us start with a simple data set. So here I have a data set of height of Indian males. Okay, so here I have, as you can see here, this is the height, and all of these are in centimeter. Okay, the height is in centimeter. Each row represents one person, one Indian male, and you have totally 10,000 observations. That is 10,000 people. So the number of observations here is 10,000. Now, of course, since these are 10,000 discrete values, you can go ahead and find simple things like mean and standard deviation. These are things that you can easily calculate, right? You have 10,000 values. You can just use the normal formula, the very common formula to find the mean and standard deviation. So here we have a mean of 165 and standard deviation of 2. 10,000 values. But notice the values, okay? 164.13 centimeter, 165.95 centimeter, and so on. So this is where I was asking the question, does it make sense to ask what is the probability of 164.13? What is the probability of 163.82? It doesn't make sense to ask this, right? First of all, let's try handling this finite amount of continuous data using histogram, okay? So height of people by itself is actually a continuous data, but practically you have recorded 10,000 observations. So in front of you, there are 10,000 discrete numbers, but we all accept and understand that actually height itself is a continuous phenomenon. So height is a continuous variable. We have picked out 10,000 observations, right? Okay. So these 10,000 observations, how do we get a sense of the distribution? So one very simple thing which we do in data analysis is histograms, right? So these 10,000 observations, you can break it up into brackets or bins. Okay, when you do histogram, generally the word used is bin. So you can break it up into bins, right? And any height that falls within a bin, you can count that height in that bin. So this way you can compute the frequencies for each bin. Right? This is what we call a histogram essentially, right? It's a frequency distribution. And we studied in the last session that frequency and probability are basically the same thing, right? So let's see what this might look like. So we took the data set, okay? We took the 10,000 people height data set, and we used Python's Seaborn library, okay, to build a histogram. And there is a parameter where you can actually set the number of bins. Okay, so suppose we divide the data into 5 bins. This is the kind of data that you're going to get, right? So here you can see 158 to 160, almost like nobody, right? This is maybe 100 people out of 10,000. Similarly, 170 to 172 also very less. And as you get closer to the mean, so mean, I think we mentioned it was 165 centimeter. As you get closer to the mean, there seems to be some pattern, right? It's like you can actually draw some kind of line like this. Now at this stage, with 5 bins, the pattern is not obvious. So let us increase that to 10 bins. So as you can see here, now I have used 10 brackets or 10 bins to visualize those 10,000 heights. Immediately I can see slightly better pattern. Okay, so if I try to, in fact, you can even just try to join the midpoints of these bars. Okay, if you just try to join the midpoints of these bars, you will get a very interesting pattern. Many of you may have seen this shape before. So slowly you will see that the shape is being formed. So in the next diagram, I have used the same data and I have broken into 25 bins. So now if you try to see, there's a very, very clear pattern which is emerging, right? Looks like some kind of mountain. Generally, people refer to this as the bell curve. We'll come to the details later. So if you take 50 bins, right, you take the same 10,000 data, break it up into 50 brackets, very, very clear pattern. Very, very, very clear pattern you can see. Okay, bell curve. 100 bins, of course, you can increase the bins also more, right? You have 10,000 data points. Why not use 100 bins, right? So again, you can see there's a very, very, very clear pattern which is starting to form, right? So let's go with the default bins. Okay, so in Python, you have an option to just go with the default bins. So in the default bin also, I am able to see this pattern. So let's just keep this pattern in mind. Okay. And of course, till now, if you see the y-axis, we are talking about frequencies. And I told you in the last session also, there's not much difference between frequency and probability. You just need to divide by 10,000, correct? So the total number of observations is 10,000. So y-axis, you just divide by 10,000. And of course, you will get the probabilities. So now you have a probability distribution. Instead of a frequency distribution, you have a probability distribution, right? Great. Notice that what have we done till now? So let's just summarize what we have done till now. Okay, we have understood that height of human beings is a continuous variable. We accept that between 162 and 163 centimeter, 162.5 centimeter, maybe somebody is there. 162.32 centimeter, somebody is there, right? We accept that it is a continuous scale. We also accept that, okay, I cannot sit and take the height of millions and billions of people. Okay, so whatever the people I have to break it into discrete brackets called histogram. The only good thing here is I can change the number of bins to see the pattern, right? This much we have done. Okay, so what are the advantages and disadvantages of this technique? All right, so the advantages are, look, we have control on the number of bins, okay, and we can specify that depending on our business problem. Perfectly fine. This is an advantage. A lot of data analysis actually uses this method, right? There is, it's not as if it's a less powerful method, right? You can definitely break your distributions into histogram buckets, and it's quite a powerful technique when you're doing in-depth, analysis in a discrete way. And if you're not thinking of your variable as continuous, that is, if you are in your problem statement, if you're thinking in terms of thresholds and brackets and that kind of thing, then of course you can use this method. But see, the disadvantages far outweigh the advantages. That's the main point here. What are the disadvantages? See, the more the number of bins, you are actually trying to store more data. The whole point is we had 10,000 observations, right? If you see the data set that we saw, it had 10,000 observations. That's a lot of observations. And in real life, we will be dealing with what? Many lakhs, many tens of thousands of observations. So that's a lot of data, computation and storage that you're asking for a simple distribution. Essentially, now that we know, okay, there is a very clear shape that is coming, why do I need to store all these numbers, all these different heights of the bars? So, the way that a histogram is displayed in Matplotlib or Seaborn, you are actually calculating the height of each bar, right? Each bar height is stored, calculated, and then displayed. So that's a lot of data computation. Whereas we know that, okay, there's a very simple but obvious pattern, right? That's a disadvantage. So there's a lot of data storage and data computation that is happening. Secondly, on a more academic and conceptual level, and even a bit realistic level, it does not capture the true behavior. So as I showed you before, we went from 25 bins to 50 bins to 100 bins. You can go to 200 bins, 300 bins, 400 bins, whatever, right? Each time your histogram is going to change. So you're not necessarily capturing the true behavior of this distribution. And however many data points you use, this distribution is still empirical. It is not theoretical. So whatever analysis you do is not universal. It is specific to your analysis. Okay, these are the disadvantages of the method that we saw. So let's, with that context, right, with that setting, with that setup, let us move into continuous probability distributions. So let's recall the empirical to theoretical in the discrete case. Okay, I'm sure that we all remember this example. So this is the rolling a fair die example. And I think this was n equal to 10, which means I rolled the die 10 times. And of course, we saw that, some numbers may come up more, some numbers may come up less, and so on. That is because you performed the experiment very less number of times. But as you perform the same experiment more and more number of times, as n approaches infinity, this is mathematics language, but practically this means what? N equal to 1000, 5000, whatever, right? You can actually take a die, take 1 or 2 hours out of your time and actually see this law in action, right? You can do it practically and verify for yourself. It will all stabilize into the same probability, right? 1, 2, 3, 4, 5, 6. They all stabilize into the same probability. This is called the uniform distribution. This is what we saw last time. The point I'm trying to make here is, instead of recording separate numbers for the different events, see, this is a very important point. In the first case, when n was equal to 10, that is the empirical case, we had to record each probability value separately for each event. But as we increase the number of trials, we saw that this random variable called number on top of a die, which is what we are referring to as the event here, this random variable, it actually follows a pattern. What is the pattern? The pattern is the uniform distribution. That is the pattern. Once you know that pattern, instead of recording 6 numbers, so on the left hand side you can see you have recorded 6 numbers. On the right hand side you have recorded only 1 number. And this is the power of the connection between empirical and theoretical distributions. It makes your analysis faster. Okay. So we saw this last time, right? You have reduced the all of this data into a simple formula. So here I'm showing you 6 data entries changed into one number, correct? My question is, can we do the same thing for continuous random variables also? So you must be thinking, you must be thinking, how is it even possible? So here we have taken 6 possible events, 1, 2, 3, 4, 5, 6. Okay, I roll the die, 100 times, 1000 times, whatever, and then I'm convincing myself, okay, I have equiprobable events, so 1 by 6, 1 by 6, 1 by 6, these are my probabilities. So I just need to remember that one number, 1 by 6. In fact, if you remember last session, I think the probability value was 1 by n, right, in the uniform distribution. So question is, can the same thing be done for continuous RVs? So in continuous RVs, what are we asking? We are asking, here it is 6 values to 1 value. In continuous, we are asking infinite values to one formula. Is that possible? The funny answer is yes, it is possible. Okay. Basically, think about this kind of data. This is our heights data. This is the height of the Indian males data. Okay. The question is, can we really have a theoretical distribution for this data? So if you remember the size of the data set, it was 10,000 data points. So question is, can we convert these 10,000 pieces of information into a single formula? Interestingly enough, the answer is yes. Okay. But before we study this distribution, we will first accustom ourselves to continuous distributions using a simple case, which is the continuous uniform distribution. Okay, which brings us to part 2. Now recall, in the discrete case we had the uniform distribution, and this is how we showed it. The random variable x follows a uniform distribution whose size is n, and then we have this probability function which we called probability mass function, which essentially maps the events to the probabilities. Now in this case, every event 1, 2, 3, 4, n, all of these are mapped to the same value, same probability, which is 1 by n. Now how did we get this 1 by n value? Look at the set of equations on the left. So it's very simple, right? You just take the sum of all the probabilities of the events, right? Probability of 1 plus probability of 2 and so on and so forth, right? And we know that this probability should be equal to 1. The summation should be 1. But we also know that each of these probabilities are equal, right? Let's call it P. So summation of P from I equal to 1 to n should be 1. This means P plus P plus P plus and so on, n times should be equal to 1. So n into P is equal to 1, P is equal to 1 by n. Very, very simple. This is the discrete case. Now in the uniform distribution, in the continuous case, what's going to happen? The graph is not going to have any breaks. Okay. So in the continuous uniform distribution, if you can see here, this is the distribution. If you can see this magenta purple color line segment, this is exactly the distribution. As you can see, there are no gaps, right? There are no gaps. There is only a range. So the distribution starts from the value A and goes to the value B. We will see an example soon, so don't worry too much about the algebra. The only difference is that first of all, it's a continuous line segment, right? So there are infinite values here, and secondly, we call it a probability density function instead of a probability mass function. Again, as I said, terminology just keeps changing, but everything almost means the same thing, so don't worry too much. But this is something we know. PDF, PMF, they all mean the same thing, right? You're trying to track the probability of a certain random variable. And the way to show this continuous distribution, the only thing that changed is x follows a uniform distribution in the range A to B. Basically, x can take any value from A to B. That's what we are trying to say. There are two values, A and B, and x can take any value from A and B. Now, given this, how would you find, first of all, how would you find the value of P in this case? Question number 1. Second of all, how do we work with probabilities in this case, right? So in the discrete case, we used summation. If you go back, this sigma operator, this is what we used in the discrete case. I think it's quite intuitive for all of us that in the continuous case, we are going to use integration, right? Summation, the counterpart of summation in the continuous case is integration. The reason for that is something called limits, which is a mathematical concept. As you increase your number of computations to infinity, the summation is replaced by an integral sign, right? But on the surface, if we understand that summation becomes integration when discrete becomes continuous, that is enough for us. So first, let's tackle the value of p. Okay, and I'm sure we all remember some of these things at least, right? How do we find the value of p? Now, this is my uniform distribution. In the discrete case, the sum of the probabilities was equal to 1. In the continuous case, the area under the curve is going to be equal to 1. So this is actually a rectangle. I know I have done integration and all here, but this is a rectangle. So the area of the rectangle is very simple, right? This is b minus a. The length of this side is b minus a, and the length of this side is p. So you don't need all this integration. You can just say length into breadth is equal to 1. Why 1? Because probability works that way. It's a law of probability, right? Area under the curve equal to 1. So I can arrive at this last equation just by using the formula of a rectangle. But I've written the integration steps because when you look at other distributions which may not have such a simple shape, you should know what's going on behind the scenes, right? And the way we do this, you integrate from a to b and you put the PDF value, that is f of x, which is the PDF value. In our case, that is p. In the discrete case also, that's exactly what you did, right? In sigma, inside sigma, you put p of x. Same thing, sum of probabilities, right? In the continuous case, same thing, integral of the probability values, f of x, right? And you just go ahead with the integration. P is a constant, it comes out, you are integrating a to b dx, which is x. You put the upper limit, lower limit, you get b minus a, and therefore you get p equal to 1 by b minus a. Okay. By the way, I should mention that I have shown you the first equation from a to b, but theoretically it's actually minus infinity to infinity. Okay. The law of the probability says minus infinity to infinity. If you integrate, then that is equal to 1. But if you see the graph, there is nothing before a, there is nothing after b. So instead of minus infinity to infinity, we are restricting ourselves to the range in which the distribution exists. Okay. Let's try to bring some example into this so that we can solidify our understanding. So consider, there's a city. Suppose there's a city and you consider the rice demand in the city in kilograms per head per month. Okay. So we spoke to many shopkeepers, we spoke to many dealers, okay, and we got an understanding. Everybody is saying that the demand in kilograms per head per month in a city of rice is uniformly distributed continuously between 3 and 6. So what are we trying to say here? The minimum that a person demands for rice is 3 kg and the maximum that person demands is 6 kg. And all the dealers and the shopkeepers and the grocers, they are saying, look, there is no difference in probability. Everyone, people are asking for 3.5 kg, they're asking for 3.2 kg, they're asking for 4.1 kg, whatever, right? So this is the understanding from the market, suppose. So then it is safe for me to say that, look, I am going to assume that the rice distribution is uniform and I know that it goes from 3 to 6 kg. This is exactly what I've shown in the graph here, right? 3 kg is minimum, 6 kg is maximum, and anything in between is allowed. So that's exactly what the distribution shows. Now, based on our formula, it's very easy to find value of f of x. F of x as in p, right? The height of the uniform distribution. That's very easy to find. Just use either you use the integration or you use the rectangle formula, whatever it is. Area under the curve is going to be equal to 1. So if you apply the formula, you will get 0.33. Okay. This much is clear, right? So this height is 0.33. This much is clear. Now the question is, what is the interpretation of P in this case? See, in the discrete case, there was some interpretation, right? Because in the discrete case, when you said P equal to 1 by n, it essentially means what? Probability of event 1 is equal to P. Probability of event 2 is equal to P. Probability of event 3 is equal to P, whatever the value of P is. There was a simple interpretation in the discrete case. In the continuous case, what is the interpretation of P? There is no real immediate meaningful interpretation of the P value of this P in the continuous case. Okay. Rather, there is another way to interpret, which we will see. More importantly, how do you even compute probabilities? Basically, my question is, if I ask the question, what is the probability that a person demands 3.2 kg of rice? Is your answer going to be 0.33? Suppose I ask the question, what is the probability person demands 4.5 kg? Is your answer going to be 0.33? How many such values are there in the interval 3 to 6? Infinite values. Each of these probabilities is 0.33. How is that possible? It's not possible. So the interpretation of P is not immediately meaningful here. But what is meaningful? So in the discrete case, it was easy. You just select the X value, random variable value, and then you find the probability on the Y-axis. This is the same for discrete uniform, discrete Bernoulli, discrete binomial. You take the random variable value on the X-axis, go to the Y-axis, get the probability, and then you can add, subtract, whatever, right? In the continuous case, generally we talk about intervals. Now see, I have given a sub-interval C and D. If you see here, there's a C and there's a D. So we can try to ask the question, what is the probability that my requirement lies between C and D? This is a reasonable question to ask in the uniform case, continuous case. And if we do ask that question, again, you can just use your integration fundamentals and all of that, or you can use rectangle formula. Essentially, what you will get is the probability that the random variable lies between C and D. That is, my demand for rice is between C kilograms and D kilograms, right? It's an interval. That probability is actually equal to D minus C by B minus A. Okay, or you can say D minus C times P. Okay, and in fact, if you try to interpret this D minus C into P in the diagram, do you know what it is? It is actually the area of this rectangle. That's all it is. Basically, we are talking about the proportion of the total distribution, right? So what is D minus C? It's this length. This is D minus C, correct? What is P? P is the height of the rectangle. So what is D minus C times P? It's essentially the area under the curve for your subinterval. That's all it is. Okay. So either you can use the integration or you can use the rectangle stuff. But generally, as your distributions get more complex, integration is required. Right. Now let's try to bring this into perspective using the rice demand example. Okay. So we know that there's a demand of rice in a city. The rice demand value X is uniformly continuously distributed between 3 and 6 kilograms, 6 kilograms. Now I can ask the question, what is the probability that the person's demand is between 3.6 kg and 4.5 kg? I can ask the question in intervals, right? So suppose we pick out any random individual from the city. I can ask this question, what is this individual's probability going to be of having a demand between these two values? This is how we analyze continuous distributions. Okay, so then it's very easy to find. So using the formula or just using the understanding, all you need to do is find the area under the curve of your interval, correct? So 4.5 minus 3.6 into the height, which is 0.33, or you can use the formula D minus C by B minus A, whatever it is, right? So 4.5 minus 3.6 by 6 minus 3, you'll get the answer as 0.3. Essentially, what we are trying to say is the probability that an individual's rice demand is between 3.6 to 4.5, that their demand lies in the subinterval 3.6 4.5 is 0.3 in this distribution. Okay, so in the continuous case, we talk about intervals. We do not talk about single values. Okay, that is the discrete case. So this is the key difference between discrete and continuous distributions with the normal distribution. So first what we'll do, I told you, we saw the heights of the Indian males data, right? And then we asked the question that, okay, I have 10,000 numbers, 10,000 values, and I'm trying to put them into brackets. I'm trying to see, is there a pattern, right? And then we saw, okay, there's a very, very nice, smooth, beautiful pattern. And we asked the question that, okay, in the discrete case, we used the connection between empirical and theoretical distributions, that is the law of large numbers. We used that connection to say that, okay, we can convert 6 values into one formula, right? 1 divided by n, for example, in the uniform distribution case, right? and we ask the question, can we do similar thing for this? Now, the basics of the continuous distributions we have understood from the uniform distribution, right? We just saw it a while ago. Let's answer that question. Okay, is there a formula for this distribution? So this is our heights data. Clearly there is some underlying pattern here, right? This much all of us are agreeing. There is clearly some very smooth, nice, symmetrical kind of pattern, right? This is generally called the bell curve. Okay. So what is that pattern? It's called the normal curve or the normal distribution. The other name for it is the Gaussian curve or the Gaussian distribution, right? It has many names: bell curve, Gaussian curve, normal curve, right? There are many names for this distribution because it's a very famous, popular and important distribution. Okay, so we have a curve which looks like this, right? We have a nice curve which looks like this. My question is there a simple formula for this PDF? Is there a simple formula for this curve? Yes, there is a formula for this curve. Okay, that is called the normal or the Gaussian distribution function. And I would say do not get overwhelmed by the formulae. I will explain each and everything. Okay, first of all, let's look at this thing here. Basically, the random variable x follows a normal distribution with mean mu and variance sigma square. Okay, this is how we are going to read this statement. Okay, the random variable x follows a normal distribution with a mean of mu and a variance of sigma square. Great. What is the formula of the PDF for this random variable? So PDF meaning P of x equal to x, but this was in the discrete case, correct? Similarly, in the continuous case, you have the continuous formula. Now, if you see, the only variable in this formula is x. Everything else is constant. See, it looks like very confusing or anything, but there's only one variable here, x. This is the only variable. Everything else is constant. Your mean is here, your standard deviation is here, root of 2 pi is here, so on and so forth. Now, what is the reason for this 1 by root 2 pi? Basically, we add this constant to make the integration value equal to 1. It makes the area under the curve equal to 1. Because at the end of the day, this is a probability distribution function, right? PDF, it's a probability density function. Then it should satisfy the rule integration of f of x equal to 1. For that reason, you have this constant 1 by sigma root 2 pi. You can see that on the y-axis here, it's generally referred to as the amplitude. Okay, but it's just a simple constant which makes the area under the curve equal to 1. The variable is inside this exponent, e power minus half x minus mu divided by sigma, right? This is where the random variable actually is there. Okay, so this is called the Gaussian or the normal probability density function. And as you can see, we already saw that the curve is, very nice and symmetric and everything. It is actually symmetric about the mean. Okay, now let's put this into some perspective. If you remember the heights data, we had 10,000 data points with mean of 165 and standard deviation of 2, that is variance of 4. So the Gaussian formula or the Gaussian distribution for the heights data is going to be the random variable x, which is height of the Indian male, follows normal distribution centered at the mean 165 with a variance of 4. Okay, that gives you this exact distribution that you're seeing. And now if you take this blue curve and you put it on this orange histogram, exactly it will fit, right? That is exactly the curve that I'm showing you here. This curve, right? The curve that we have estimated, which perfectly fits this distribution of the heights. That is the curve that you will get using this formula. F of x equal to 1 by 2 root 2 pi. This 2 is nothing but the standard deviation. Okay, into e power minus 1 by 2 x minus 165 divided by 2. As you can see, this 165, this is the mean, and you can see here 2, this is the sigma or the standard deviation. Okay, and of course you can also see the y value here, but as we saw before, the y value by itself does not have any meaningful interpretation, right? If you remember the p thing that we discussed in the uniform case, by itself the p value doesn't have any meaning. We have to talk in terms of intervals, right? Okay, before we move on with that, one thing is very obvious here, that the center of the normal distribution is also equal to the mean, equal to median, and is equal to the mode. Now in this case I have taken 10,000 data points, so some bins seem higher and some bins seem lower, and you might say that the mode is to the left or mode is to the right. But if you increase this 10,000 to 1,000, let's say 1 lakh data points, then all these bars also will start going inside this purple curve, and you will get, you know, almost perfectly it will fit inside the purple curve, right? So the mean and the median and the mode, all of them will lie exactly in the center, which is 165, and quite obviously the curve is symmetric. Okay, left and right, it is symmetric. The Gaussian curve is symmetric. Now see, this is where things get a little bit interesting in the normal distribution. The role of standard deviation. Okay, so mean, we know it is in the center. As you can see, I have put a straight line at mu. Please see the x-axis. This is mu. Mean is in the center. And we know that the normal distribution is symmetric. Left and right, it is symmetric. Okay, what is the role of standard deviation? Now, after appreciating and acknowledging that yes, this distribution is symmetric, and by the way, you can verify this from the f of x mathematics formula also. Okay, even from the formula you can prove that it is symmetric. After seeing that it is symmetric, I have put some things on the x-axis. See the x-axis. This side I have mu minus sigma, this side I have mu plus sigma, mu plus 2 sigma, mu plus 3 sigma, mu minus 2 sigma, mu minus 3 sigma. Okay, basically I have taken random variable values, one standard deviation away from the mean on right side, left side, 2 standard deviation away from the mean, right side, left side, and so on. Okay, the very interesting part, right, the very interesting part in this is that you can see percentages and proportions of these values exist in the intervals. So basically about 34% of your data will always lie between mu minus sigma and mu. This is true of all normal distributions. So my height case, the mean value is 165, right, for my 10,000 data points of height, and the standard deviation value is 2. What I am saying is 163 to 165, right, mu minus sigma comma mu, this interval, right, heights between 163 and 165, people with heights between 163 and 165 in a large population will always be 34% of that population. All normally distributed variables behave in this way. So it is symmetrical. So now you can see on the other side also, mu to mu plus sigma. So 165 to 167 centimeter. People of height from 165 to 167 centimeter in a large population will always be 34% of that population. Okay, and see, these are all pre-calculated values. Okay, we'll come to how to calculate these values and all that. We will come to that. Okay, the answer is integration. Obviously, we just saw in the uniform case that we just need to integrate the area under the curve, nothing else. So mathematically speaking, the area under, for example, this shaded region, the area under this shaded region is 34%, 0.34. So if you do the mathematics, you will get 0.34. Okay, the area. But the interpretation should start making you think, you know, a little bit. So if a variable is normally distributed, then this is always true. Okay, regardless whether you take the, you know, samples from, you know, different samples from the same population. Like if I have, so India has what, 1.5 billion people, right? So from this, if I randomly select even, let's say 1 lakh, 10 lakh randomly, always this rule will be true. Okay, and of course there are more intervals. So from mu plus sigma to mu plus 2 sigma, it's about 13.5% of the population, and so on. Okay, these are pre-calculated and always true values. So in the heights, so basically you if you want to think of as symmetric intervals, then mu minus sigma to mu plus sigma, 68% of the population lies here. Mu minus 2 sigma, mu plus 2 sigma, 95% of the population lies here. Mu minus 3 sigma to mu plus 3 sigma, right? 3 standard deviations away on both sides, 99.7% of the population lies here. Okay. So what does this mean in the heights case? So as you can see in the diagram, and here are the numbers, people between 163 to 165 centimeter height, 34% of the population. Therefore, the probability that a person will have between 163 and 165 centimeter, what's the probability? 0.34, right? That is the way to interpret this normal distribution, correct? And of course, you can take any interval and you can answer these questions. Okay. So see, till now you were using pre-computed values. Okay. These values actually came from integration, of course. Now I think it's an understatement when we say integration of, what was that, e power minus 1 by 2 x minus something something square dx. Of course this integration is going to be complex, right? So that's why we have those pre-computed values. In fact, if you Google right now, just Google normal distribution, you will get the same numbers. Just go to Google Images, okay, and just Google normal distribution, okay, and you will get these numbers: 34, 13, 2, 99, 95. You will get the same numbers. So these are all pre-calculated, okay, and we agree that this integration is messy, which is what I've written here. The integration becomes very messy. And so what? So now if I ask you the question, what is the area under this part of the curve? So as you can see, I have two numbers. I have 162.3 and I have 168.6. And if I ask you, what is the probability that x lies between 162.3 and 168.6, how are you going to do it? You don't have the pre-computed values, right? This is not exactly minus 1 sigma, 2 sigma, right? It's random two numbers. We need to put the value in the integral, right? We need to put these here. I need to put 162.3 and here I need to put 168.6 and then I need to integrate. Of course, this is messy. This is messy, but since this is universal, statisticians and data scientists have universally come up with something called the z-score and the z-table. We will come to this very soon. This is kind of like a logarithm table. If you remember in high school and all, we used to use this log anti-log tables, right? Now actually calculating log to the base of 2 of 23 and everything, the calculation is so complex. What is the meaning of log? 2 power x is equal to 23, right? So if 2 power x equal to 23, then x is equal to log to the base 2 of 23. Now to calculate this, how are we going to do it? We used to use log tables, all pre-calculated values. Since the normal distribution is so universal, and again, I will give the example soon. Since the normal distribution is so universal, statisticians, mathematicians, data analysts, data scientists have come up with a universal table of these values. Okay, so we'll get to that very soon. Before that, we should understand the implications of this. See, what are the normally distributed data in real life? A lot of the variables that people deal with in different fields, be it medical, transport, finance, economics, governance, a lot of these variables are normally distributed. It is something that naturally arises in nature. The normal distribution naturally arises. So heights are normally distributed, birth weight is normally distributed, job satisfaction measure, these are normally distributed, runs scored in cricket matches, age of people, salaries, IQ scores, so many variables in so many domains are normally distributed. Not uniform, not anything else, normally distributed. This bell curve. Okay. So my question is, does the previous method of simplifying this vast amount of data safely into single formula? Now, what is that single formula? In the heights case, where was the formula? Where was the formula? Let's see the formula in the heights case. In the heights case, this was the formula, right? F of x equal to 1 by 2 root 2 pi e power whatever, and you put the mean value and the standard deviation value in the correct places. Okay. Does this work for all these other things? Age, birth weight, salary, and everything else? Yes, Answer is yes, exact same formula works here. Some examples, and I've given the links also. Age of Nobel Prize winners. As you can see, this is normally distributed. Okay, the mean seems to be around 60, and I guess the standard deviation is maybe 10, 15, something like that. From this distribution, looks like 15 or something years is the standard distribution. Okay, age of Nobel Prize winners. There was one study on the length of housefly wings. Okay, the length of the wings of housefly. This is also normally distributed. Okay. Then there is one study on the distribution of shoe sizes, right? So this is also normally distributed. In fact, this link, I think there are many more examples. You can check that. Salaries also are normally distributed. Now this graph is a skew normal. Okay, this is what we call skew normal. So skew normal analysis is a bit out of scope of this session, but suffice to say that if I take care of some of these outliers, if I just take care of some of these outliers, the remaining data will become perfectly normal. If I just remove some of these outliers, remaining data will become perfectly normal. Okay, so many of these real variables are normally distributed. And interestingly, and this is the funny part, this is actually why are we studying all this? Why did we study discrete distribution and empirical and all of that in the last session? Then why did we study normal distribution, continuous? Why did we study all this? This is the main thing. There is something called the central limit theorem, which you will study in the next session. I believe the session is dedicated to central limit theorem. There's a theorem, okay, in mathematics statistics, which ensures that sampling distributions are normally distributed. In other words, even if your population is not normally distributed, you can devise your sampling technique in such a way that the sampling distribution is normal. So there is a lot of motivation to study the normal distribution. Even if your data is not normal, you can work with it in assuming the sample is normal, which not an assumption, sorry, making the sampling in such a way that it is normal. Okay, so more on the central limit theorem in the next session. Okay, but suffice to say that this normal distribution is almost everywhere when you deal with real variables. Okay, so now there's an interesting thought, right? Now shoe size, age, height, salaries, cricket runs, whatever, right? There are many real variables which seem to be normally distributed. Now each of these has a different mean and variance. Yeah, we saw height's mean was 165. I think the mean was 60, and different variance values, right? Can we transform all of these normal distributions so that a single formula can represent all these? So right now we need to specify the mean. That is, in height's case, 165 centimeter was the mean, and standard deviation was 2. And in another case, the mean was 60 and the standard deviation was 15. Age of Nobel Prize winners, right? But since all of these have the same pattern, is it possible to transform to some kind of new distribution with single formula for all these distributions? The answer is yes. Okay. And what are the motivations? Why should we do that? See, you can start comparing variable distributions more easily. Okay, cross comparison becomes very easy. That's one motivation. It allows for simplification of computations. If you saw those values initially, 68%, 95%, and all these values, they are just 2-3 values for 2-3 intervals of this thing that we call the Z table. We'll come to that soon, right? Here I've written Z table. So it allows for making the Z table in the first place. Once we have this universal kind of distribution formula, from that we can generate Z tables. I'll show you how to use that also. And it also enables the generalization of statistical rules. So data scientists and statisticians, when you do hypothesis testing, which you will be dealing in the next week, there are something called significance thresholds. Okay. Now, these are many of, and all of these normal distributions, if there is a single formula or a single distribution which can represent all of these, then you can have a single significance threshold. I am happy with 95% confidence, I am happy with 90% confidence, whatever, right? Some of these things you will study in the future sessions. So there are many such motivations to try to find this formula, and that's called standardization. This process is called standardization. Okay, and the mathematics on the screen may look very complex and messy, but it's very simple. The main thing that we need to see is the substitution in the middle. So on the left hand side you can see this x, that is the original random variable x. So that is the height of the person. It could be 163, 167, whatever. That is the x. Mu, that is the mean of your data. In the heights case it is 165. Okay, and sigma, that is the standard deviation of the data. In your heights case that is 2. All you need to do is you need to make this substitution. Okay, this x minus mu divided by sigma, which is there inside this formula here, substitute with z. And of course internationally z is pronounced z, which is why we call it z score, z score. So please don't mind, sometimes I'm saying z, sometimes I'm saying z. Okay, so you need to make the substitution, and this is exactly what we call the z score. Z score is nothing but x minus mu by sigma. Okay, it is a transformation. You're converting x to z. You do that, and then interestingly your distribution now has zero mean. Why it has zero mean? Try put x equal to 165 in this. 165 minus 165 is 0. So wherever originally you had 165, now it is 0. Okay, so the new distribution is centered at 0, and the standard deviation sigma becomes equal to 1. Okay, it's not 2, it's not 15. So standard deviation was 2 in the case of height, standard deviation was 15 in the case of age of Nobel Prize winner. Now with this distribution, all standard deviations for all of these different variables become 1. So the full mathematical proof is out of scope, but there are some links that I've given. So I believe you'll be getting the PDF. So in your free time, you can go through the links. Okay. What does all this mean? So let's recall the normal distribution for the height data. So as you can see here, it has mean of 165, variance of 4. Okay, and in the formula we have x minus 165 by 2 here. That x minus 165 by 2 replaced by z, and if you replace by z, if you do the transformation, then your distribution, the normal distribution, becomes something that we call standard normal distribution. Okay, standard, it's there in the word itself, right? Standard, it is standard across all the normally distributed variables. It is standard. They all follow the same distribution, and this distribution is independent of the mean and the variance of your original data, right? Because the mean of this distribution is 0. It is centered at 0 always, and the variance is 1, or standard deviation is 1 always. So in the x-axis you don't have minus 1 sigma, minus 2 sigma, that is mu minus 1 sigma, mu minus 2 sigma. No, you now have 0 minus 1 into 1, which is minus 1, then 0 minus 2 into minus 1, which is minus 2. These are very, very, very simple values to work with. They are also universal. Okay, everything on this slide is not just representative of Indian male height. This is true for any normally distributed data. Okay, great. Now that brings us to something called the Z table. So we have seen that many real variables more or less follow the standard normal distribution. Now, if we have a quick way to calculate the probabilities under the standard normal curve, right? So basically in this curve, if somebody can give me a very, very fast way, quick way to find the area under the curve for different intervals, right? For different intervals, if there is a simple way to calculate these probabilities, then I can answer a lot of questions. Many questions can be answered. Why? Because many real variables are normally distributed. So I can answer questions like, what's the probability that an employee of a certain company has a CTC between 5 LPA and 15 LPA? Random question, but I can answer it. What's the probability that a random student I select for a candidate for basketball team has height between 163 and 166? Again, random question, but I can get the answer, right? All of these are normally distributed, and if I have a simple way to calculate these areas, then I can answer these questions confidently. Okay. Now let's go back to the heights problem, in which I told you that we had these two two values, 162.3 centimeter and 168.6 centimeter, and that time we did some quizzes on 163 to 167, 161 to 169, the very common intervals. But what about random intervals, right? So we said, okay, integrating this is going to be messy. So how do we calculate this probability? So basically the question is, what's the probability that an Indian male has a height between 162.3 centimeter and 168.6 centimeter? That's the question. If I had a quick way to get those probability values, then I can answer this question. Okay, so let's go to this step by step. The first thing that you need to do is standardize your normal distribution. So as you can see, the original value was 162.3. Okay, how do you standardize? Subtract the mean, divide by the standard deviation. Okay, x minus mu divided by sigma. This is called the z-score. Basically, I think, yeah, there's a mistake on the x-axis. It shouldn't be x, this is z. Okay, the x-axis variable is now z. If I standardize it, it will become z. Okay, so anyway, minor thing, but I hope the point is very clear. The x-axis, originally it was the original variable. After standardizing, it's now z. So for all the different distributions, you have the same x-axis. For height, for housefly wing length, for age of Nobel Prize winner, for anything normally distributed, after this transformation, x-axis is the same, z. Okay, minor mistake on my part. Please ignore that. The x-axis should be z. Okay, so how do you standardize? X minus mu divided by sigma. So 162.3 original value minus mean 165 divided by sigma 2. This gives me a z-score of minus 1.35. Okay, then for what about 168.6? 168.6 minus mean 165 divided by 2, standard deviation. This gives me 1.8. So the first thing you do is standardize this. Next, what is your question? You want the area between this, right? Now, in the normal case and in the standard normal case, both cases, area under the curve, total area is 1. So whatever area you calculate here is the probability in the normal distribution also. So basically, I've just divided this into two parts, which is easier to do the calculation, right? So I have one region here, let us call it region A, and another region here called region B. So basically, my objective is to find A plus B. What is the area under A plus B? That is going to be my probability value. Okay. Now, this is what we call a Z table. Can everyone tell me if it's somewhat visible at least? See, the Z table is actually very large. Can you please let me know in the chat, are you able to see the numbers in the table? Yeah, visible? Great. So how do we read this table? Okay, how do we read this table? What we need to understand here is, you might be wondering, the first value in the table is 0.5. That itself is a bit weird, you might think. Why is it not starting from 0? Right? Why is it starting from 0.5? The reason is that the normal curve is symmetric. It's symmetric. Okay? And your z-score is centered at 0. So what the table is showing is additional to the left hand side. Okay, so this whole thing, right, this whole thing on the left hand side, whatever the area is under the blue curve, is 0.5. Obviously the total area is 1 and the curve is symmetric across the mean, so left side of the mean has to be 0.5, obviously. But the mean in the standard normal case is what? It is 0 because of the standardization process. Therefore, if you see here, for z equal to 0, for z equal to 0, the number starts from 0.5. It is giving you complete area from left hand side up to the z point. So completely from left hand side up to z equal to 0 has to be 0.5. Correct? In this case, completely from left hand side up to z equal to 0 has to be 0.5. So that is what you're seeing in the first cell, 0.5. So how do you read this table? If you go left to right, you will say, for example, just take the first row, 0.0, then the next one is 0.01, then the next one is 0.02. These are the z-score values. Okay, if you take the second row, it starts with 0.1. So then when you go to the right side, you will get 0.11, 0.12. So these are the columns. As you can see, it says plus 0.03, right? So choose the first decimal point vertically, then choose the second decimal point horizontally. Okay, that is how you read the table. So essentially, it is giving me the area under the curve from minus infinity, that is full left, to the z point cutoff. And we know that the curve is symmetric, so we should be smart enough to use this table. Let's look at how to do the calculation here. Okay, so let's just concentrate on A for the moment. See, if I flip the curve left and right, still the table will be the same. So minus 1.35 and 1.35 both will be symmetric. So where is 1.35? 1.35 will come somewhere here, right? This is going to be 1.35. So for me, if I want to calculate this part, I need to do what? I need to calculate basically this part. Okay, let me just this is a bit critical part, so I'm going to do this visually. Give me a second. Yeah, so as I said, it is symmetric left and right. So let's just take this, right? I need to find out this area, and then I have to subtract 0.5 basically. Now you must be asking, the z table is giving me from left hand side, will I get the same value from right hand side? Yes, the standard normal distribution is symmetric. So if you split if you switch this, and instead of minus 1.35, if you go for the value 1.35, you will essentially get the same result that you're looking for. So from the right hand side to the z value, in this case what it is, minus 1.35, is the same as from left hand side to positive 1.35, same. Okay, so let's go back to the z table. What was the value? 1.35 is the z value. So where is 1.3? Where is 1.3? Here you can see 1.3. There's the go vertically and search for 1.3. Then you have to add 0.05. So this column, right? This is plus 0.05 column. So essentially we are looking at this value here. Okay, this is the area under the standard normal curve from full left to positive 1.35 or from full right to negative 1.35 because of the symmetricity property. And what is that area? 0.91149, and that is exactly what I have written here. Okay, so from the full right up to minus 1.35, that value is 0.91149. It's a probability value. Okay, cumulative probability value. Minus what? Why minus 0.5? Because I need to cut off this value, right? First I need to calculate A, so I need to cut off this value. And what is this value? This is the middle value. From extreme right to 0 has to be 0.5 because total is equal to 1. Very simple. So the area under the part A is 0.91149 minus 0.5, which is this value here, 0.41149. Okay, so basically 41% of my population is in the region A. Okay, so let me just erase this part so that things are a bit clear. Okay, right. So I now know that 41% lies between the center, that is 0.5, and the z-score minus 1.35. Basically z equal to 0 to z equal to minus 1.35. I have 41%, 0.41149. Same logic for 1.8. What do you do for the region B? Calculate the area under the curve from negative extreme minus infinity to 1.8 and then subtract 0.5. That's all. So Can we see the Z table and see how to do this? So go vertically, you will find a row which is Z equal to 1.8, and the value, and it is 1.80, right? It's not 1.81, 1.82. So go for the first column, and the value here is 0.96407. All right. So that's the value I have here, and then you just subtract 0.5 because you're trying to find only the area under B, and the Z table is actually giving you from negative extreme to 0.8, right? It is giving full this much area it is giving. So we have to subtract the 0.5, right? This part is 0.5, and that value is 46%. Okay, so therefore the area under the region B is 46%. So now I have both my values. The area under A is 41%, the area under B is 46%, and you can see the computations on your screen, right? So we have here 0.41149, 41%, 0.46407, 46%. You just add it and you get 0.87556. Okay. And now all you need to do is you need to essentially just go back to your basic distribution, the normal distribution, and you can make the claim that about 87.56% of Indian males have the heights between 162.3 centimeter and 168.6 centimeter. In other words, we have essentially found out the area between the value of 162.3 centimeter and 168.6 centimeter. And what does area under the curve mean? It is essentially the probability. The probability that a random Indian male, you can see the statement in the bottom, probability that a random Indian male has a height between these two values is about 87-88%. Let's look at a quick use case. See, suppose you're a data scientist, okay, or a data analyst working for a high-end clubhouse, okay, and suppose that the clubhouse requires 20 security personnel or 20 security persons, and they have received 2000 applications. Okay, you need 20 security people, you have received 2000 applications. The clubhouse is asking you to come up with a suitable height threshold. Now, for some reason, the clubhouse is thinking that height is a good feature or good variable with which to threshold the job applications. Of course, this can be different in your domain, right? If your domain is different, then you might be using other metrics, okay, salary, experience, whatever. In this case, the clubhouse is saying use height as a threshold and come up with a suitable cutoff so that you reduce these 2000 applications to 50 applications. Maybe because clubhouse does not have the time, okay, they cannot go through 2000 applications. They saying, okay, give me 50 applications. How do you go about doing this in a very fair way, right? So let's take the height distribution here. Okay, let's take the height distribution here. Now what does the normal distribution tell us? We have 2000 applications. The mean height is 165 centimeter. We know that the normal distribution is symmetric. Therefore, I can confidently say that about 1000 of the applications have height less than 165 centimeter, and about 1000 of the applications will have height greater than 165 centimeter, half. Okay, because 165 is the mean. And these 2000 applications, the heights of the security people, the 2000 applicants, is following the normal curve. So if I set a minimum threshold of 165 centimeter, I can cut off 50%, right? So I will say everybody below 165 centimeter height, do not take the application. So out of 2000, you are left with 1000. Great. But what was the question? The clubhouse wanted me to reduce 2000 to 50. So obviously this threshold is not enough. Okay. Suppose I go to 167. If you remember, 167 is mu plus 1 sigma. So my mu is 165. My standard deviation is 2 for the heights data. So 167 is basically mu plus 1 sigma, 1 standard deviation further. And we know that the chunk has 34% or something, right? If you remember the normal distribution chunking of plus 1 sigma minus 1 sigma, about 34% after the mean. So if you set the min height at 167 centimeter, then 50 plus not 34. I don't remember exactly, but we should check the number. Okay, if you set the minimum height at 167 centimeter, you will be left with 32% remaining applications. Okay, in fact, let's essentially go back and check. Believe it is 34. Yeah, 34%. Okay, so 50% is here and 34% is here, right? Okay, there's a small error in this slide. Yeah, forgive me. There's a small error in this slide. So this is 50% and this is 34%. Okay, so the remaining is not 32. That's my bad. Okay, it should be 50 plus 34 is how much? 84%. So remaining will be 16%. Okay, so if I move the minimum height threshold to 167, which is 165 plus 1 standard deviation, 165 plus 2 is 167. The total area under the curve till 167 is 50 plus 34, 50% plus 34%, 84%. So I'm removing 84% of the 2000 applications. 16% will remain. So it's not 640, that's a mistake. 320 applications will remain. Okay. Again, what was the original question? 50 applications. So let's move this even further, right? Let's go to mu plus 2 sigma. So 165 plus 2 into 2, which is 2 into sigma, which is 169 centimeters. So suppose I set my threshold at 169 centimeter and I say everybody less than 169 centimeter, just reject the application. Now again, the normal distribution tells me what? It tells me that only 2% afterwards will be left. So about 98% of these applications we are rejecting if we set the threshold at 169. So now how much will remain? 2%, which is 40 applications out of 2000. Okay, but the original question was 50, not 40, right? So I went too far. Okay, so till now we are doing trial and error. Okay, but should we always be doing trial and error? Like, see, again, for example, if I just say, okay, 169 centimeter became too much because only 40 applications remained, so let me reduce that a little bit to 168.5 and see what happens. And if you do reduce to 168.5, what you should do? Standardize this value. 168 minus, you just do the standardization. 168.5 minus 165 divide by 2, go to the z table. I've written the steps in the bottom. Go to the z table, calculate z score, get the probability, and you do all of these things. You will essentially get 80 applications. Okay, so if you use 168.5, you will find out that 96% is on the left side and 4% is on the right side. But should we be doing trial and error so much? No, there is actually a very easy way to figure this out. How do you do that? See, the full thing is in this slide. We want 50 applications out of 2000. What's that proportion actually? 50 by 2000. So if you do 50 divided by 2000 into 100, you will get 2.5%. Basically, we want to retain 2.5%. So we need to find a z-score, that is, we need to find a height threshold that covers 97.5% on the left side. So we need a z-score that gives me area under the curve of 0.975. Now you can of course look at the table and see which z-score gives me 0.975. Okay, let's go see the original z table. Where is the z table? Yeah, here's the z table. So I want 0.975. Search the z table. Where is 0.975? Here it is. See, somewhere down in the corner bottom right, you can see 0.975. Which z value is giving me 0.975? Just check the row and the column. 1.9 and 0.06. So 1.96. So by quickly looking at the z table, I know that the z score of 1.96 gives me 97.5% on the left side. So I know that the z score I'm looking for is 1.96. Now remember the transformation formula. Z is nothing but x minus mu by sigma. So just rearrange the terms. What you will get? X equal to mu plus z sigma. That's all. So you can go from original variable to z score. Same way you can go from z score to original variable. Okay. So let's revise this. Okay. We want 2.5% to be retained. That means we want 97.5 to be rejected. Therefore, we want the z score whose area under the curve on left side is 97.5%. That z score from the table is 1.96. Using that, I can convert the z score back to my original using the substitution formula, z equal to x minus, in this case 165 divided by 2, right? 165 divided by 2. And what is the z score? 1.96. So x is equal to 165 plus 2 into 1.96, which gives me 168.92 centimeter. So if I set my height threshold at 168.92 centimeter, I am more or less ensuring fairly that my 2000 applications reduce to exactly more or less 50 applications. Okay. So if I set the threshold at 168.92, this gives me 2.5% on the right side, which translates to 50 out of 2000 applications. Okay. So of course you can extend this to any domain, right? It's not just number of applications or anything like that. Heights of people, you can expand this to any normally distributed variable and make these kinds of decisions. Okay. All right. So I hope we have understood the use case, and I hope that all of you can take what you learned from here and go and see with your own domains, with your own kinds of data, where these normal distributions are arising and how decisions are being made using the distribution. So just some closing comments from my side. Many real data are normally distributed, like height, birth weight, and so on. We saw that. Normal distribution can be used to analyze data and provide more confidence in decision making, which is what we saw, a very simple use case just now, right? It will be different in different domains, but it provides confidence in decision making. Okay. And not just that, the normal distribution plays a very central claim in something we call inferential statistics, okay, which is making claims about population based on sampling, okay, which is the central theme of your next session, in which you will be learning central limit theorem and things like that. So I mean, the normal distribution is quite important in statistics, data science, for all these reasons. Okay. Thank you very much for attending the session. I hope that this has been enriching and enlightening.
We have covered the fundamentals of probability distributions. Probability distributions help us make sense of uncertainty and variability in data, which is essential for statistical analysis and machine learning. This video has given you a solid foundation in statistics upon which you can build further. Keep practicing and don't hesitate to ask questions. Thanks for watching, and please subscribe to our channel.